Hello everyone and welcome to this video. In this video we will talk about beta function, and then we will see its property, that is symmetry, and then we will move to different forms of it. So let's begin. I will begin by introducing you to the definition of beta function, and then I will discuss symmetry, that is if we interchange the arguments what will happen, and then we will see different forms of it. So let's start by giving heading. So let's say let me quickly write beta function. Beta function. So let's define it quickly. There is nothing in the too hard in the definition that needs to be discussed. So there are two arguments of the function, L and M, and it is defined as an integral from 0 to 1 x to the power L minus 1 and 1 minus x to the power m minus 1 dx. This is how the function is defined. So don't ask questions like why it is like this. It is just defined like this. So let's start by discussing an important aspect or property known as symmetry. So let's start with beta of L comma m is equal to, I am rewriting the same thing again just for this result to be a thing of itself. So if we change x to 1 minus y, like if we are making x as 1 minus x, I am trying to do that. So if we change x to 1 minus y to make it resemble this term, then what will happen, that dx is equal to minus dy, and from here we can write 1 minus x is equal to y. From if we substitute these values over there, we will get beta of L comma m is equal to integration from 1 to 0. If we put the values 0 over here, y will be 1. If we put 1, y would be 0. So the limits has been reversed. So if we put x as 1 minus y from here, and 1 minus x as y, and in place of dx minus dy, I'm writing minus sign over here. Now I will utilize this minus sign to reverse the limits of the function. So if I do that, it will become 0 to 1. If I write this term first, m minus 1 and 1 minus y to the power L minus 1 dy, which is nothing but beta of m comma L. Why? By definition it is. It doesn't matter if it is x, y or t. It's an definite integral. So variables doesn't matter. Just the form matters and the limits matter. So y, x doesn't matter. So a very important result, that is beta of L comma m is equal to beta of m comma L. That is, if we replace if we interchange the arguments, the value of the function doesn't change. Or if some question is given to you, say beta of 2 comma 3, you can write it like 0 to 1, x to the power 2 minus 1 would be 1, and 1 minus x to the power 3 minus 1, that is 2 dx. This is what you will write if by definition you would see x to the power first argument minus 1, 1 minus x to the power second argument minus 1. That how it is defined. But even if you interchange the powers or these terms, the same thing, x to the power 2 and 1 minus x to the power 1 dx, the results doesn't change since the values of these two are same. Okay, so this is what symmetry means, that if you interchange the arguments, the value of beta function doesn't change. So let's move to some other forms of beta function. This is what how it has been defined, but the variables may be changed with some other substitution. So we will see some other forms of beta function. This is the other form of beta function. So what I will do, I will try to solve this as a proof question. So you may sometimes in the examination you may be asked with some proof like this. So I will try to solve it like prove beta of L comma m is equal to this much, and it is nothing but other form of beta function. Okay, so let's start with the standard definition of beta function, that is beta L comma m is equal to integration from 0 to 1 x to the power L minus 1 and 1 minus x to the power m minus 1 dx. Okay, so if I substitute x with 1 divided by 1 plus y, why like this, why how what happened? So if we can see that there is 1 plus x term in the denominator. So here in the standard definition of beta function there is no such variable. So I am trying to create that kind of variable over here. So let's start with this substitution. So if dx is 1 by 1 plus y, then this implies that dx is equal to minus dy by 1 plus y squared. And if x is 0, that means y must be infinity, and if x is 1, that means y must be 0. So limits would be from infinity to 0. In place of x I would write 1 by 1 plus y to the power L minus 1, and from here I can write 1 minus x as 1 minus 1 by 1 plus y, and it is 1 plus y minus 1 by 1 plus y, and it is y by 1 plus y. So it can be written as 1 minus x can be written as y divided by 1 plus y to the power m minus 1, and in place of dx I would write minus dy divided by 1 plus y squared. Okay, so let's use this minus sign to reverse the limits 0 to infinity. In the numerator we just have one valuable term, that is y, because since 1 raised to power anything would be 1, and I have utilized this minus sign to reverse the limits. So all that remains is y. So y to the power m minus 1, and in the denominator we have 1 plus y terms. So let's add their powers. 1 plus y to the power L minus 1 from here, and m minus 1 from here, and 2 from here. and dy. So we will get 0 to infinity y to the power m minus 1 dy divided by 1 plus y to the power l plus m. And you know, since it is a definite integral, you can always change the variable. It doesn't change the value of the function. So you can write it as x to the power m minus 1 divided by 1 plus x to the power l plus m dx. And this is what we needed to prove, and this is what the result is. This is other form of beta function. And one more thing you can say, that m minus 1 you can also write it as since beta of l comma m is equal to beta of m comma l, you can always rewrite it as is equal to 0 to infinity x to the power l minus 1 divided by 1 plus x to the power l plus m. If you interchange l and m, you will get this. And it is also, so you can write any one of l or m in the numerator, and since you had to add both of them, so it doesn't matter in the denominator. So that is what I wanted to convey. So this is the second form of beta function, and you can replace m and n in this because of the symmetry. Okay, so let's move to the next form of beta function. So next topic is beta function in terms of gamma function. So if you have any difficulty in gamma function and you have not watched my videos, you can definitely check out my videos, which would be linked somewhere around this video in the I button over there in the corner, or if not there, it must be inside the description box, so check out in the description. So let's start. Before the relation between beta and gamma function, let's start with integration. That is, I is equal to 0 to infinity e to the power minus ax x to the power n minus 1 dx. This is the integration. Okay, so if we replace ax from t, we'll get x is equal to t by a, and dx is equal to dt by a. And if we substitute all these values in I, we will get 0 to infinity e to the power minus t by a to the power n minus 1. In place of dx, we will write dt by a. Okay, so let's clean this up. So a to the power n minus 1 in the denominator and 1 more in the denominator would be n. So 1 by a to the power n, 0 to infinity e to the power minus t to the power n minus 1 dt. And this integration is nothing but definition of gamma of n. So gamma n divided by a to the power n. So gamma of n divided by a to the power n is equal to integral 0 to infinity e to the power minus ax x to the power n minus 1 dx. So this is the result I would proceed with in the relation to come up with the relation. So it was very important to discuss this first in order to achieve the results. So you need not to write this in the proof if you ask to prove the relation, but you should know this how we achieve this result. Okay, so let's start with the proof of relation between gamma and beta function. So let's say gamma of L by z to the power L is equal to 0 to infinity e to the power minus zx. From the previous relation that I am writing this one in place of a, we have z now, so x to the power L minus 1 dx. Okay, so if we put this z to the power L in this side of the equation, we will get gamma of L is equal to 0 to infinity e to the power minus zx, x to the power L minus 1, z to the power L dx, and then we will multiply both sides with gamma of L, will multiplying both sides with e to the power minus z and z to the power m minus 1 is equal to 0 to infinity e to the power minus zx, x to the power L minus 1, z to the power L, and e to the power minus z, since we are multiplying it in both sides, z to the power m minus 1 and dx. Then I would integrate both sides with respect to z. So let's write it over here, multiplying both sides by e to the power minus z, z to the power m minus 1, integrating both sides with respect to z. Okay, so let's start with LHS, gamma of L. If we integrate the whole thing from 0 to infinity, e to the power minus z, z to the power m minus 1 dz is equal to 0 to infinity for z, for x, e to the power minus zx and e to the power minus z, so we have e to the power minus z 1 plus x over here. Okay, so then we have z to the power L plus m minus 1, and we have x to the power L minus 1 dx dz. Okay, so in this side, since gamma of L is independent of z, so I can write it outside the integration. And on the RHS, if I see only the parts where z exists, then I can integrate that part as 0 to infinity for x, since x is still dependent on z. But for this part, I can write x to the power L minus 1 outside the dz integral, since it is independent of z, and write inside e to 0 to infinity for z, e to the power minus z 1 plus x z to the power L plus m minus 1 dz, and then for whole dx. So I can integrate this part separately, since rest of it doesn't depend on z. Okay, so it would be x is equal to 0 to infinity. Again, using the previous result that we obtained, like this one, where a is 1 plus x over here. So I can write it as, first write this part L minus 1, and for this part I can write gamma of L plus m divided by this term, a term, plus x to the power L plus m. From the previous result, dx is equal to x is equal to 0 to infinity. Since gamma of L plus m is independent of x, I can write it outside, or maybe I can just put it on the RHS, and I just forgot to do this step on the LHS. So gamma of L, so this can be written as gamma of m. Yes, and in this step I can take this thing outside the integration and then put it in the LHS. So gamma of L, gamma of m, and then gamma of L plus m. Okay, and here I can write x to the power L minus 1 by 1 plus x to the power L plus m dx, and this is nothing but the second form of of beta function that we just discussed previously. And we can see that gamma of L, gamma of m divided by gamma of L plus m is equal to beta of L comma m. And this equation also follows symmetry. Since gamma of L and m are in multiplication, we can always replace L and m and the results won't change. And in the denominator it is in summation, so we can also change in the denominator. So symmetry also follows in this part as well. Now we will discuss how we can write these kind of integrals in terms of gamma and beta function, and in some way we can say that this will become some kind of form of beta function. So I am discussing this as well in this video. So let's begin. So let's say it is I, and what we need to prove, like to make it as like a proof question. So say if it was asked that it is proved that is equal to gamma of p plus 1 by 2 gamma of q plus 1 by 2 divided by 2 times gamma of p plus q plus 2 whole divided by 2. So this is what we will obtain at the end, and you can see it is beta of p plus 1 by 2 and q plus 1 by 2 divided by 2. So this is what we will obtain at the end, but let's see, I wanted to show you what it will result into first, so we can begin. So let's say we want to achieve that, so we can substitute sine theta or sine square theta as t. That means 2 sine theta cos theta is equal to dt, and if I move these terms to that side, then d theta is equal to dt divided by 2 sine theta cos theta. According to our substitution, we can write it as dt divided by 2 times, since it is sine theta, so it would be root t, and for cos I can write under root 1 minus sine square theta, so 1 minus sine square theta would be 1 minus t under root, so this will give us cos theta. So our substitution is complete. Let's substitute the values in the integral. For I is equal to, if we put 0 over the value of theta, we will get 0. If we put pi by 2, we will get 1. In place of sine to the power p, we can write it as, we can alternatively write it as 0 to pi by 2 sine square theta to the power p by 2. If I square it over here, I can write, and these powers will cancel out. And similarly, cos to the power q by 2 and d theta. So in place of sine square, I can write t to the power p by 2. In place of cos square, I can write 1 minus t to the power q by 2. And for d theta, I can write dt divided by 2. Root t can be written as t to the power 1 by 2 and 1 minus t to the power 1 by 2. So if we clean this up, we will get 1 by 2, 0 to 1, t to the power p by 2 minus 1 by 2, p minus 1 by 2, and 1 minus t to the power q minus 1 by 2. These 1 by 2 come from the 1 by 2 in the denominator over here, and dt. Okay, so now you can see this is beta function of, for arguments p minus 1 by 2 plus 1. So p minus 1 by 2 plus 1 would be p plus 1 by 2, and similarly it would be q plus 1 by 2. So beta function can be written as, in terms of gamma function, as gamma of first power plus 1, so p plus 1 by 2 multiplied with gamma of q plus 1 by 2, and divide the whole thing by gamma of sum of these two, so that would be p plus q. If I write these terms first, and then 1 plus 1 would be 2 whole divided by 2. So you can write these kind of integrals, that is sine to the power p and q to the power cos to the power q, in terms of gamma function like this, and it is also equal to 1 by 2 beta of p plus 1 by 2 comma q plus 1 by 2. So that this is what we achieved. So I said that it in some way can be treated as another form of gamma function. So if we take beta of L comma m, then if we put this 2 to the other side, that would become 2 times integration of 0 to pi by 2 sine to the power something and cos to the power something d theta. Let's try to find out what something is. If I put L in place of p plus 1 by 2, if it is equal to L, then p would be 2 times of p plus 1 would be 2L, and p would be 2L minus 1. And for q, similarly, q plus 1 by 2 is equal to m for our substitution over here. So q plus 1 is equal to 2m and q is equal to 2m minus 1. So it would be sine to the power 2l minus 1 and cos to the power 2m minus 1. This is the beta function in terms of sine and cosine, that is trigonometric functions. But the more important result is this one that you should remember. We'll solve questions based on this, nor this one. The questions would be mostly from this one equal to this one. So in next session we will discuss value of gamma half again with the help of beta function. Since we derived some result over here, we will use this result to find the value of gamma of half, and then we will see duplication formula and some other formulas relevant to the beta function and gamma function. Thanks a lot for watching this video. I will see you in the next one. Bye bye.